In this video, we are going to talk about fundamental principles of pyrometallurgy, and our field of study here is going to be Ellingham diagram. So one may ask, what is Ellingham diagram? So when we talk about Ellingham diagram, it's a plot of free energy change as a function of temperature. So it's a plot of free energy change, so free energy, which is Gibbs free energy change as a function of temperature. And one may ask, what is Gibbs free energy? So when we talk about Gibbs free energy, energy is a measure of the thermodynamic driving force that makes a reaction to occur. So this Gibbs free energy make a reaction to occur. So in that case, we have some condition under which a reaction will occur. So when the Gibbs free energy is greater than 0, term it as non-spontaneous. In that case, the reaction will not occur at this condition. So we have the first condition. With the second condition, when the Gibbs free energy is less than 0, we term it spontaneous. And in this condition, the reaction will occur. And the third one is when the reaction is at equilibrium, that Gibbs free energy. Now, let's look at the equation for the Gibbs free energy. That's for the change in Gibbs free energy. And with that equation, we have that change in Gibbs free energy is equal to change in enthalpy minus temperature change in. Now, let's move on. Now, what we are going to learn now is how we can construct the Ellingham diagram. So we are going to look at the construction of Ellingham diagram. Construction of Ellingham diagram. Now, change in Gibbs free energy versus temperature plot can be drawn as a series of straight line. So in that case, change in what Gibbs free energy here as a function of temperature can be drawn as a series of straight lines. So when you plot it, you get a series of straight lines, right? So that is how we will see the lines on the Gibbs free. That is the Ellingham diagram. That is how you see it. Now, the slope of the line changes when any of the materials involved melt or vaporize. So when the material is melting, the slope of the line, you see some change to dots. That signifies that the material is going under a condition, maybe melting or vaporizing. Yeah. And one thing we should also know that the Gibbs free energy is negative for metal oxide, right? The Gibbs free energy is negative for metal oxide. So for metal oxide, the Gibbs free energy is negative because we want the reaction to occur. Now, what does the Ellingham diagram shows us? The Ellingham diagram shows us metal reacting to form oxide, sulfide, and what? Chlorides. So we will see that on the Ellingham diagram, there are metals that are reacting to form metal oxides. Metal oxide. Also, we have sulfide and chloride. But mainly, the Ellingham diagram was designed for most oxide. So the Ellingham diagram was designed for most oxide. Now let's look at the Ellingham diagram, a sample of the Ellingham diagram. And this is a sample of the Ellingham diagram. But this does not contain all the metal oxide here. So we have some part of it here. So now, we want to know the use of this Ellingham diagram, which is the uses of this Ellingham diagram. What is even used for? Why do we need to study this? So the first thing is that one, the Ellingham diagram predicts which reducing agent can reduce which oxide and at what temperature. So this is the Ellingham diagram. We want to find out which reducing agent can reduce the metal oxide for us to get our metal and at what temperature. So the first one is we finding the reducing agent suitable for reducing the metal oxide. And also the second one is we determine the partial pressure of oxygen that is in equilibrium with the metal oxide at a given temperature. So as you can see that we have 1, here, this, let me write it well. It's PO2. That is partial pressure of oxygen, right? That is in equilibrium with the metal oxide at a given temperature. And the last one, we also we use Ellingham diagram for. This is for partial oxygen. And the third one is we also help us to determine the ratio of carbon monoxide, which is carbon monoxide, this one, carbon monoxide to carbon dioxide. That will what? Be able to reduce the metal oxide at a given temperature. So at a given temperature, this will carbon monoxide to carbon dioxide will be able, we want to know that will be able to reduce the metal oxide at that given temperature. So now let's look at the ease of reduction. Now, so you know that Ellingham diagram will help us find the reducing agent. That means that when it's undergo oxidation, we get a reducing agent, right? Yes. So the ease of what reaction is, reactions close to the top are most noble metals. So when you take the Ellingham diagram, the reactions that are close to the top are most noble what metals. Are most noble metals, and these noble metals include gold, platinum, etc. And their oxides are unstable and are easily reduced. So with most noble metals that are close to the top in the diagram, their oxide are unstable. So their oxide are unstable, and then they are easily reduced. So the Ellingham diagram help us find a reducing agent that can reduce the metal. When we talk about this, like the metal is in the oxide state. In this case, we want to get that metal out of the oxide state. So then we want to come to the Ellingham diagram and find which metal can be used to reduce that metal oxide to get their metal from that metal oxide, right? Yes. So now let's look at something. I'm now coming to explain how we can find a reducing agent. At a given metal, so at a given metal, let's use calcium. At a given metal can reduce the oxide of all metal whose line above DS on the table. So on the diagram, let's see, this is the diagram, and we want to know which metal can be used to reduce it. So then when you come to that, let's start with what? Calcium. Calcium can be used to reduce magnesium in magnesium oxide. This is because calcium line is below magnesium line. Same applies to magnesium, can be used to reduce titanium because magnesium line is below titanium line. And let's go again. We can also have that zinc. Calcium can be used to reduce zinc because calcium line is below magnesium line. That is it. And but zinc can also be used to what? Oxidize calcium because it's above the calcium line. Let me take it again. What I'm saying is that for us to find a reducing agent, the line must be below the metal of interest you're looking for. So if you want to reduce aluminium in aluminium oxide, what you need to do is that we need to find the metal which are below the what? This reaction line. Are you getting it? Yes, which are below this reaction line. And which metal are below? We have magnesium and what? Calcium. That means that magnesium can reduce aluminium, right? In aluminium oxide. And also calcium also can do the same work to reduce what? Aluminium. Now let's take one example. They are talking about they were saying that magnesium, right? Magnesium can reduce titanium oxide. Titanium. Let's see that. Can magnesium reduce titanium oxide to titanium? Now let's see that. So you go back when this such question is given to you, you go back to the Ellingham diagram. Then you locate these two lines of magnesium and titanium. So we have this line which represents, so this line represents the magnesium line and this line represents the titanium line. Now the question is that can magnesium reduce titanium oxide to titanium? Now we go down there. We know that now magnesium is below the titanium line. That means that magnesium can reduce titanium since it's below the titanium line. Are you getting it? So magnesium can what? Reduce the titanium line. Now let's try and find the overall reaction. Let me teach you how we can find the overall reaction. After you've established that it can reduce that. Now, when writing the reactions, right, on the line, you need to write the reactions. What you do is that for simplicity, you will write it as it is here because one is above and one is below. So then we are going to look at the one below. equation will come below, and the one above equation will come above. So what we do now is that we know that titanium is above, so we have titanium plus oxygen giving you titanium oxide. This is equation 1. And the line below here is what? Magnesium plus oxygen giving you magnesium oxide, equation 2. So that means that the magnesium is now coming to reduce the titanium oxide to titanium. So now we've established that this can reduce since the line is below. Then after you've done that, what you do now is that you reverse equation 2. So when you reverse equation 2, you're going to get that 2MgO will give you 2Mg plus oxygen. And in that case, then you sum. This is be equation 3. So what you do now is you're going to add equation 3 to equation 1. The oxygen is going to cancel the oxygen. And then when you add them, you're going to have that the total for this reaction, overall reaction. Let's look at the overall reaction. For the overall reaction, we know that we get titanium plus 2MgO giving you titanium oxide plus 2Mg. Let's do the reaction very well to see. When you do it very well, we'll now know that when you have TiO2 plus the magnesium metal, it will reduce it to titanium plus 2MgO. We've established that what they're asking is that can magnesium reduce titanium oxide to titanium? Yes, because the line is below the titanium line. And we established the overall reaction that for here, when titanium oxide reacts with magnesium, we are going to get the titanium. So magnesium has now reduced the titanium oxide to titanium. That means that magnesium can reduce the titanium oxide to titanium. Let's look at another second example. Can calcium reduce manganese oxide to manganese at 800 degrees? Now we are going to look at the full diagram, the full Ellingham diagram. We're going to look at the full Ellingham diagram. So let's look at the full Ellingham diagram. It's here. Yeah, this is the full Ellingham diagram. So for the Ellingham diagram, this is a complete Ellingham diagram that you see. So when working with it, this is what you are going to work with it, right? So this is the full Ellingham diagram, right? So for the full Ellingham diagram, this is the Ellingham diagram. The question we're asking us is that we are using this to answer it. That can calcium reduce manganese oxide to manganese? And if your answer is yes or no, you put down there. So before you to have your answer to be yes or no, you need to go back to the Ellingham diagram. Now we are going to locate the calcium line and the manganese line. So we know that the calcium line is this line. We have this line to be the calcium line, and the manganese line. Right. So now they're asking us that at 800. So the temperature given to us at 800 degrees or 1073 Kelvin. When they give it in Kelvin, you need to convert it to degrees because on the Ellingham diagram, we do is degrees, right? So then you will trace your line, which is 800. You trace it. Let's trace it. This is 800. You trace it to hit the two lines. So now it hits manganese here and it hits calcium here. Then you come to the second one, that which one can reduce which one. Now, since the calcium line is below the magnesium line, it means that the calcium can be used to reduce magnesium oxide to manganese. Okay. Since the calcium line is below the manganese line, it can be established that the calcium can be used to reduce manganese oxide to manganese. This is because the calcium line is below, right? So when it is below, it means that it can be used to reduce that. So in that case, when you are done, we are supposed to write the overall reaction. So first, I established that when you're writing it, the one above is what you write first. So you write the one above. And in this case, the one above is the manganese. So 2Mn plus oxygen giving you 2MnO. And then we have the calcium to be 2Ca plus oxygen giving you 2CaO. Then this is equation 1 and this is equation 2. So you reverse equation 2. When you reverse equation 2, you're going to get CaO giving you 2Ca plus O2. And in that case, the oxygen will cancel the what? Oxygen here. And we add equation 1 to equation 3. Equation 1 to equation 3. What you're going to get is 2Mn plus 2CeO, CaO, giving you 2Ca plus 2MnO. And in that case, what you've established here is that, let's do it correctly. So that'll be 2CaO plus 2MnO, giving you 2Mn plus 2Ca. Now, in that case, we have established that calcium has now reduced the manganese oxide to manganese. So the answer is yes. You write your answer, yes. And when you write your answer, you will show the overall reaction, which is, this is the overall reaction of it. That shows that calcium can reduce manganese to manganese.